So what I always would recommend you do is, in this case, figure out what the undistorted spring length is. So the undistorted spring length is, it already had, when it was at 4/10 in length, it already had 1/10 of a meter stretch in it. So it's going to be 4/10 of a meter minus that stretch that exists. So the undistorted spring length is 3/10 of a meter. Okay. Now we're going to have to draw, I'm going to just go ahead and draw the picture. And I believe they call the distance down, or I called it distance H, coming down from that horizontal position. Distance H. Then the springs are going to be of this dimension. So the spring length then is going to be equal to the square root of 0.4 squared, which is 0.16, plus h squared. Also, they told us that the velocity right here was 2 meters per second. And they were asking the question of what the speed is when it's 0.3 meters. H is 0.3. Okay. So the speed we're looking for is when h is equal to 0.3 meters. And the mass was 2 kilograms? No, 10 kilograms. Thank you. So we have mg is 10 times 9.81 or 98.1 newtons.
We assume these springs are often light. So if
we assume the springs are massless.
Need we?
Excuse me? Need we?
Yeah.
Yes. Because things get a lot more exciting if we allow for something that's got distributed mass in motion. It's in rotation as well as in extension. Okay, so the analysis would become significantly more involved to allow for the inertial effects of that rotating mass as well as the changing length of that mass, if you account for the springs. Okay. So this is oftentimes, the way we're doing this is oftentimes a first cut of an analysis that you would want to do if you wanted to get much more refined with it. So you'd take a first pass at it this way, and then you would go in and start embellishing it with more detail. Okay. And that would be appropriate in some cases. Okay. Feeling pretty good? Not too bad. The only thing we're going to add to this problem is we've still got a condition of conservation of dynamical energy because there's no friction, no cables hooked on with some forces in them. So we still got a case of conservation of dynamical energy. Delta T plus delta VG plus delta VE equals 0. One-half our mass. 10 times V at H squared minus V initial squared plus 98.1 is the weight. We need to set a datum. Why don't we set the datum up here? At this level. So we have, what are we going to put for the
0,
position final
negative h.
down here?
Negative 0.3.
Excuse me?
Would it be negative 0.3?
I don't want to do that. I want to use this.
Oh, h.
Negative h. It's below the datum. That's negative h. Okay? And then we're going to subtract from that the height it happened to have from the datum initially,
Which is at the datum, so.
which was 0. Right at our datum. And as you should be able to look at this in the math and tell, once again, like we did in the last question, that you're dealing with a giving up of a negative potential. It's a loss of potential. You should check this stuff as you're writing it and see that exists there. Similarly, you should look at, when we write down this elastic change in elastic potential energy, you should look at the expression you get and see if it feels right, given the behavior of the springs. So we're adding to it now 1/2. The stiffness was 800 times the delta at h squared minus the delta initial squared. And that overall sum of those changes in energy has to equal 0. Feel good? So let's keep these terms separate so we can keep an eye on them. So here's the velocity at location h minus our initial velocity was 2 meters a second, I believe. So we have 5 times that difference. Here we have minus 98.1 h. And over here we have plus 400. Now, what about delta h? Might even want to go up here and do a little side calculation for delta h. So let's look back at our picture. When it's down here at this physical position at location h, when it's down here at location h, then we want the distortion that exists in this spring. Oh, and as a matter of fact, what's missing over there? There's a spring here, and there's a spring there. Okay. What I wrote over there was one spring. Yeah, so we just have to double that up, okay, when we get back over there. So what I'm looking for is what's the distortion in the spring when it's in this position between my fingers?
L. There it is.
No, distortion.
L minus
L minus the original spring length. Okay, so it's this radical minus that original spring length, which we computed as a 30% of a meter.
Should it be L minus 0.4?
Well, because it was already distorted 0.1 of a meter.
That's going to be
Right.
That's going to be in our second part of that.
Oh, okay.
Yeah.
Gotcha.
Okay, so then we're going to have the radical of 0.16 plus h squared minus the undistorted length. And then h initial, or excuse me, delta initial is going to be the 4/10 spring length minus the undistorted length, or 1/10 in value. So we're going to be using this value and that right here in this equation. Okay. In years past when I've taught this, I have not emphasized that distortion fact, and then I give an exam and 2/3 of the class screws up on that. And so that's why I'm giving you guys that insight, so you'll be able to do the work properly. Yeah.
If we did that as an integral, right, instead of doing the change in the deltas, would we have to account for the distortion, or could we just put in the initial and final lengths of it?
You can work them up as integrals, but it would be a heck of a lot more work for you. I think it's much simpler to just do it in the generalized based on the geometry that we see here with the radical.
Sure.
Yeah. Okay. So what I have to do now, don't forget, is we've got 2 springs there. So let's come in here and make sure we clarify that there's actually another factor of 2 in there. So that's going to leave an 800 sitting here times this then. And so this expression gets pretty messy sometimes, and you can see it's that radical minus 0.3, that quantity has to be carefully squared, and then we can subtract from that this delta 0.1 squared, which is just 100. And that's got to be equal to 0.
Shouldn't it be 0.1 far right there?
You squared it, right?
I squared it.
Oh, already? Okay.
Yeah. Thanks for keeping an eye on it, because I screw this up all the time. It's arithmetic. And I know you folks don't. Okay. Now, look at the structure of this equation. If we solve this for VH, it's going to turn into a big radical, isn't it? With radicals inside it. The radicals inside it. And I think it might be worthwhile. Let's go ahead and finish the problem. Let's find the velocity of h when h equals 0.3 meters. And so that's going to imply that we're going to drop this stuff in and move these things over to the other side. So if we do that, if I leave this structure and take this to the other side, that just reverses these terms, right? This becomes a positive, and this term becomes a negative.
Yes.
Okay, if I take that to the other side. So and I'll leave the positive 800 on there. So if I take that over to the other side, VH with h equals 0.3 is going to turn out to be, and I'm going to take this over first, 800, and I'm going to end up with 0.01 minus, and then when I square my 0.3, it's 0.09. And I add those together and I get 0.25 right there on that radical under the square root minus 3/10. That has to be squared. And then I'm going to move the 98.1 times 0.3 to the other side. And that turns out to be, with a 0.3 here, what do we get? A little under 300. Somebody punch that quick. 98.1 times the 3/10.
29.43.
I'm sorry, yeah. Almost 30, yeah. 29.43.
43.
And that becomes positive. Thank you. And then we're going to move negative 20 to the other side, becomes plus 20. And then we're going to divide this whole thing by 5, and then square root. Now, I don't recommend you do things this way. Okay. I'm just doing this for the efficiency of time efficiency here. It's much safer for you just to take each piece and work it up. and then carefully move things around. If you then punch that result out, you should end up with the value of the speed. What would you expect? Speed up or slow down from its initial?
Who knows?
Okay, we've got 10 kilograms, which is fairly sizable weight, 20-something pounds, already moving at 2 meters per second, and it's got these springs on there, and we want to let this thing move on down 0.3 of a meter, and then the question is, how powerful are those springs compared to the gravitational effects? If you had a real soft spring, it might be speeding up because of the domination of the gravitational effect. Or if they're real stiff springs, the springs might overpower the gravitational effect. Okay? So there's a balancing act going on. Did I write down an answer?
Looks like you got it at the bottom right.
Yeah. Now, I don't think this will show up on the image of the DVD. So what I want to do is I want to sketch what I've done previously with this. Is I actually took this equation and solved for V as a function of H and plugged it into the graphing calculator and let H vary and drew a graph which looks like something like this. And it's actually got it goes down to, because of the radical underneath there, it goes down here like this. Makes no sense to be over there. Well, actually it would. It would be mathematically, it would be up above the datum. Okay? And then here the velocity was 2. And the graph, well, actually it continues up. Yep. It actually continues up a little bit and then dies. And here is, well, let's see. No, I'm sorry, it's not the maximum there. It's actually over here. This is where 0.3 of a meter H value is, and the speed right there at 0.3 of a meter turned out to be 2.255 meters per second. And with a graphing calculator, we're actually able to figure out the location where it has its V max, which I did not do, and I don't have it stored in my calculator still, unfortunately. And the H position at which that V max occurs. So it's kind of interesting. Initially that spring, we can come back over here and look at the picture. Initially, there's not much energy stored in the spring. There's only 1/10 of a meter extension in the spring. So there's not a whole lot of energy there. And what happens in here is the gravity dominates it, causing it to speeding up. And then once the spring starts to become long enough, the spring forces start to counteract that gravitational force. Make sense? And then it starts to cause it to slow down. So somewhere down in here, the thing's actually moving quickest. And when it gets down to its 0.3 of a meter, it's got this speed that's a little bit slower, 2.255 instead of the maximum speed. Okay? Well, it's fastest here. It's fastest somewhere in here, and it started to slow down, and it gets to 2.255, which is still greater than what it had here.
But it is faster than.
And we could. Now what happens is it's going to slow down and eventually stop. We could run that problem by zeroing this term out, couldn't we? and find out what H value does this mass come to rest. And then what would it do once it got down there?
Turn around.
Go back up.
Yeah, let's come back to the picture here for a second. It's going to come down to a maximum, and then it's going to come speed back up, coming back up. Have a maximum speed again, probably in here, right? And then when it gets to here, what's it going to do? On the way back up.
Past that point at
How fast?
2 meters a second. Hasn't
2
lost any
meters per
energy.
second upward. And then it's going to go on up here and do similar kind of behavior. It's going to be a simple harmonic oscillator. Mm-hmm.
Do you chance remember the height of that Vmax?
I did not write it in my notes there, and
I think that would be if you just took the mass, let go of it, let it sit there, that height's where it rests at. Because a harmonic oscillator will pass its maximum velocity
correct.
at its equilibrium point.
At its equilibrium point, exactly. And that's a good observation, and you guys have done that in physics before, where you've looked at those. And so the equilibrium spot would be where Vmax would occur, if you just carefully let this mass move down until the spring force has balanced it. Okay. You know, with it to only have 5 minutes left, T1, I'm going to call it F1 and F2. Right? And these are spring forces, aren't they? Some K delta. Some K delta. And this is going to be sitting at some geometric position. Right? And actually, I don't want to confuse the force with the geometry. Right? And so here's your radical here on your geometry, this and this. And so what we could do is write the vertical sum of forces here for static equilibrium. Summing forces y equals 0 for the static condition. Then we're going to have the vertical component of this is going to be K delta is the force, and the sine of, the cosine of this angle, which is h over the radical of 0.16 plus h squared. That's the cosine of that, and we have to double that spring force minus the weight, so that must equal, this must equal the weight, 98.1. And delta is what? Delta in the spring is the radical minus the 0.3, right? So we have 2 times the stiffness is 1600, and then we have the radical is the minus 0.3 times h over the radical, and that's got to be equal to the 98.1. I've got 2 minutes left. kicking that radical in the denominator over to the other side, that's going to be 98.1 of the radical, and we can take that away from 1600 and move the, oh, we got an H in there too? Oh, that makes it a little more exciting. Okay. That doesn't clean up quite as nice. Well, I'll tell you what, because of the time issue, you can see you could solve this problem for H. And we should get an answer that is in that region between those two spots. It should be something less than 0.3 here. And so if you want to take a little extra moment or two after class, you can go ahead and work that solution up, and you should get an answer that's right in here. And that would be the place, like you observed, where the body would sit in static equilibrium, balanced by the spring force and gravity. Okay? I think we have to cut it off. Okay, that's it for today.